Good morning. We will wait for 5 more minutes. Let other students join.
Sorry.
So let us start. So today we are going to see the elastic and highly available and resilient infrastructure for varied application scenarios on Microsoft Azure. So the basic compute and all the details we have seen in case of Azure, as well as AWS and Google Cloud platform also. But how to design elastic, highly available and resilient infrastructure. So by using these three basic advantages of all these scenarios or public clouds, how we are going to develop different varied applications on this. So that part we are going to see now. So for that purpose, first of all, we'll go through this.
Good afternoon. Oh, come on. Good afternoon. Thank you. And thank you all for coming today and spending your afternoon. Better content for all of you. PaaS services. PaaS services, for the most part, take care of the high availability themselves. There are some things you can do there, but if you have questions about that, ask me afterwards. But I'm really going to spend most of my time talking about doing infrastructure as a service and how you do that with high availability in Azure. And with that, let's get going. High availability. What does it mean to you? Everyone actually has a different definition of this. I mean, if you think about uptime, ask yourself, what's the availability of the application that you want to do? And that's a business requirement. I won't drill in too much into how you define that because it's going to be different for every person in this room. But basically remember that you're going to define what that is, and that's going to define how complex a system you want to build, how many nines you want to be designed for, what level of fault that you want to be able to handle with your system.
Highly available.
And so think about what those different things are, because it's going to alter what architecture you're going to use. And we'll talk about a number of different architectures today and how you'll use those different architectures to solve for different levels of faults that you might have happen within an organization. This is part of the resiliency continuum, so some of this is kind of foundational. I just want to make sure we're all on the same page about stuff. So resiliency continuum is basically everything that has to do with keeping your applications online. This talk talks all about high availability. I'm not going to talk about backup or disaster recovery. There's some links at the end of this deck that will talk about sessions that cover that content, and other talks here at Ignite that you can check out that will cover those. But the thing that I want you to take away is basically RPO and RTO. That's recovery point objective and recovery time objective. For high availability, the target is 0. So the goal is basically you are always online, and any fault that happens does not take your system offline. And that's what we're going to talk about designing systems for today. If you're in a situation where those have gone offline, you're in a disaster recovery scenario, and you can check out the talk that was done yesterday that talks about those pieces on it. So think about how do you make sure that as things happen, as servers go down, as disks fail, as you get high levels of traffic, that you can make sure that your services continue to serve up the applications that you've built. So when you think about the cloud and you think about doing that, you need to start thinking about something that, for anyone who's worked in manufacturing, anyone work for a manufacturing company? Quick check. A few folks in the crowd. You're probably very familiar with Mtbf, mean time between failure. But that's what you need to start thinking about, because you're going to have a lot of different servers. And as those servers run, you're going to think about how long does it take between when these things fail. And the reason you want to think about that is the higher that number is, the bigger the amount of time between when things fail, that's how less likely that failure is to occur, and you need to think about that when you're designing for your availability. The more rare that occurrence is, the more you have to decide, is it worth the cost of designing a system that's going to protect you from that? The more common that failure is, the more you're going to want to be able to build a system that's able to handle that. Something like a disk failure or, say, dropped packet in a network might be fairly common, so you want to make sure you design for that. Something like a data center burning to the ground hopefully is a very uncommon thing that happens for you, and so you have to decide, do you want to be able to design something that spreads across regions, multiple data centers? We'll talk about all those different designs and how you do it, but you'll make those decisions because they'll impact the cost and the design of your architecture, how complex it is, how many different things you need to manage and set up automation for. This is true for on-premise and on the cloud. Obviously, we'll be talking about the cloud here, but a lot of the principles and the design techniques we talk about will be the same, although the technology that I'll be showing you is how Azure does those things and makes it easy for you. And just remember, failure of hardware is inevitable. When we say Mtbf, that's mean time between failure, because everything fails at some point. Never assume that nothing will ever, something will always be available. Something will fail always. It's just a question of when, so plan for it. So some good design principles when you design for the cloud, and you think about kind of, okay, what are the things you should think about architecturally? You think about doing it. And we'll step through a bunch of these, and then we'll drill in deeper into actually talking about how you actually make them happen. But if you take nothing else away from this talk, no single point of failure. So I run into this one all the time when I'm talking to people, and everyone conceptually gets that, right? If you've got one machine, we've been doing this for years on premises, you always have two machines, and you link them together to make sure you have no single point of failure. Remember that it's not just the virtual machines you need to think of, it's everything in the infrastructure that you're building. We'll talk later on about how to make sure you don't have single points of failure in storage. When you think about what you're doing in networking and load balancing, so you have no single points of failure. It's no single points of failure throughout your entire stack. And again, when you talk about that blast radius of how big a event you want to protect yourself from, you also need to think about what does that mean in terms of, is a region a single point of failure for you? Do you want to be able to survive something like a region service disruption? Because that's one single point. And if you want to do that, there's some design characteristics that we'll talk about how you build those systems. But again, different systems, different size of scale that you want to be able to design for. Next one is your state should stay at the edges of your app stack. When I say app stack, it's important to think that it's not just the edge. You don't want that always on the client, but you think about basically the ends, so basically your presentation layer, your client, or the database layer. Don't put it in the middle. You want stateless services. So make things as stateless as possible. Best place usually is to store your state in a database. If you're something that does a lot of transactions moving fairly quickly, you may decide to put your state in something like a NoSQL database versus storing, say, your transaction data or your financial data and put those in something like an RDBMS, a SQL database. But you don't have to pick one database. You pick the right thing, but make sure you store those in one particular location. Don't store them, don't store them throughout the app. If you create stateful applications, you're creating things that are brittle. You're creating things that when those pieces of the application fail, your customers will be impacted. So keep your state away from the center of it. It will allow you to be more scalable. It'll make it faster, and we'll talk about that. Talk loosely coupling your components. If at all possible, make sure they're loosely coupled. What do I mean by that? Is if you're going and you're passing state along through, so you've got a monolithic 3-tier app. Everyone's built one at some point, 3-tier app? Yes, hopefully. We'll talk a lot about those. When you have a 3-tier monolithic app and you're storing state, like you store state on the server, then if that goes down, you're impacted. It also means that if something else in that stack goes down, if things are reliant upon that, you've impacted everything in that chain. If you make things loosely coupled, then losing one part doesn't fall away from somewhere else. So this is a little bit more of like a service-oriented architecture or microservices. We'll talk about both today, but if you think about it, if you take microservices and basically instead of passing things between load balancers, which is typically what you'll do between tiers to make sure you have scalability, you're going to use things like queues. Because if you put it in a queue and that next tier isn't available for some reason, it'll just stay in the queue, and when that next tier becomes available, it can pick it up. You're resilient to that failure that happened, versus if it goes to a load balancer and there's nothing below that load balancer, if that tier has failed for some reason, then your service is offline. And it didn't matter that your other tiers were available because you've lost it. Your customer packet just goes to nowhere and dies. So think about using queues instead of load balancers. It does require a different bit of architecture, and you have to choose what's right for you. But that will help you build things that are loosely coupled versus strongly coupled. Process your content centrally and then deliver it locally. So if you're think about your data. If you distribute your database everywhere, you're going to have all these little bits that you have to piece together. It's super easy with the cloud to put it in one place, process that, and then send the data places where you want to deliver it. So if you have all your data in one central place, you're going to avoid some of the challenges that you have with databases of spreading them out. We'll talk later about how if you need to spread them out for any number of reasons, including disaster recovery, how you do that. But that's going to make it more complex. Again, everything's on a continuum of the complexity of the cost you're doing versus your ability to move quickly and easily. So you process it centrally, but deliver it locally. And whether that be making sure that you're processing that data and then, say, putting it out to a storage file that you pull it out of, or you have a secondary database that you actually put that data available in locations that are closer to your customers, or whether it be using something like a CDN and actually having the CDN cache that content that's closer to your customers. They'll get a better experience out of it. You'll get more scalability out of it. And we'll talk a little more about that later in the presentation. Finally, just a good kind of, or not finally, but next one is a good rule of thumb about automating. Make sure you automate everything. I know, especially when you're doing development, super easy to go in there, make a quick configuration change, or just develop and push it. It's a bad habit. It's fast, it's easy, it's not repeatable. If you take a look at failures that happen with systems, if you take a look at even data center level failures, if you take a look at industry-wide statistics, data center-wide failures, over 50% of them are human error. People make mistakes. We should manage code. Code should manage machines. Get in that habit. You'll be able to be more scalable. You'll be more available. You'll be able to bring your systems up faster. Do that, and we'll talk a little bit about how you can do that in Azure and using ARM templates to do it. Me personally, I'm a fairly trusting guy, but stick with trust and verify. Everything you do, make sure it's actually happening. We'll talk about how you monitor your services a little bit. We'll talk about what you're doing with load balancing, make sure things are up. That you have to make sure that not only you've built the system that you intended to build, but that you're verifying that that is happening and that it's staying that way. And there's a number of different services that you'll verify different ways, and we'll talk through each of those about how you do that and make sure that you're doing it. But you have to verify not only that your system is there, but it's delivering what you want it to do. And the last one is really one of these big changes that's happened as you move to the cloud versus and you bought the biggest database server you could. And you bought the biggest database server you could because you can't scale the database server. Technically you can go and you can shard it, but that's a whole lot of work that you probably don't want to do unless you hit the point where you have to. So you bought a really big box and it was probably highly underutilized, and you made sure that you put the best drives you could, that you got the best network cards, you put redundant power supplies in it, you did everything because you needed to take care of that server. And that was scaling up. And if you hit the point where all of a sudden you reach, because that cost that you do isn't a linear. Remember, hardware will fail. Bad things will happen. You'd be going in there and you'd be fixing that server because that server is something that you needed to take care of. And that's the version. You've got your patches and you're going to go patch that server. What do? Because when you go and you build a new application, you can follow the principles that we're going to talk about in this talk. And you can build it so that it's built for the cloud, that you're using the right principles to make sure that it's scalable, that you're taking advantage of all of what the cloud provides to you. If you're using something that's software that someone else built, it can be designed for the cloud. If you are, then you're fine. But a lot of legacy applications, how many people run an application in an organization that is at least, say, 6 years old? So those are going to be a little bit more challenging because they probably weren't designed for a cloud. They probably were designed for horizontal scaling within an organization. Now you can lift and shift those to the cloud, but what you're going to do to maintain high availability with those is going to be different. You're going to have to think strongly about the database layer when we talk about databases and how you make sure that the data availability is there. But there may not be a lot that you can do for, say, the front end or the logic tiers. If they've designed those to be stateful applications, they are somewhat brittle, and there's not a lot that you can do about it because you don't own the code for that. So you're going to have to think about that as you design and as you think about what's the availability targets that you're doing with those older applications if you lift and shift them to the cloud. So the last one is designing around a single state data store. That's what we talked about before, about making sure that you're storing state and you're keeping that in a data layer, that you can keep your applications as stateless as possible because that's going to give you the most flexibility and ability to scale and handle faults as they happen. So today's talk, we're going to go through 3 basic areas: compute, networking, storage. These are 3 kind of core areas for your infrastructure, and these are 3 different areas where you can have faults that come in, you can have failures that happen, and how you're going to design and protect around each of them. You could have a fault happen in any one of them, or, due to my awesome PowerPoint animation skills, you can have faults in all of them. So let's talk through what you can't move it into one. You'll have to recreate the machine in the availability, create a new one, or if you're doing it command prompt or in an ARM template, you can just create it there, but you have to make sure. And when you spread yourself across fault domains, that means that you've eliminated the. So if there was an unplanned failure or a particular VM, then when you start up the second VM, so we got the front end like we had before, but now you'll notice there's a second load balancer. We're using an internal load balancer. So now we've got separation between 2 tiers. We've got a data tier, which means that the 2 SQL databases are not up at the same time, or they're up at the same time, but the data is not synchronized. And you'll also notice that in the second region, we have many less machines. It's not that it's the same design in both places. You have what's kind of like a pilot light. You have another region that's set up, and if you need to, you can scale it up when you need it, but you're not running a bunch of infrastructure for no reason in that second one. That's an active-passive design. We'll talk about both active-passive and active-active a little bit later, but that's the dead giveaway in this one. So I talked about VM scale sets, and I want to drill in a little bit more on that. This is your way to do auto-scaling in Azure. So we talked about the cattle. You have the same set of VMs, so it's by tier. The same way that you did your availability set, same kind of rules apply. So you're saying, hey, this is my web tier, this is my logic tier, whatever it is. It's the machines that are all the same, and you'll define that. You'll define the operating system for it, both Windows or Linux, that you're going to be using for that. And you'll define the rules around how you want that scaling to happen. You can do this through an ARM template. You can also do it through the portal now. There's portal experience. And you can set things like, what's the maximum number of machines I want to set up? This is really useful for protecting yourself from things like, because the way it scales is you can set it for some sort of metric. So let's use CPU utilization as a good metric. And you say, hey, if I'm at 75% CPU utilization or more, I probably want to scale up. So start up another machine. So go spin another one up. And you can say the inverse as well. If my machines are running at less than 10% CPU utilization, these are configurable, of course, then I want to scale down, take one out of the set. So you can scale, but it also gives you a maximum limit. So let's say you had a bug that pegged your CPU. So it spins up another machine, hits the bug, pegs the CPU, another machine. You don't want to wake up in the morning and find out there's 1,000 machines that got spun up simply because it just kept scaling and scaling and scaling. So we give the ability for you to put a cap on it. And you can set up monitoring as well, and so you can be alerted if something's happening. But we give you the ability to kind of protect yourself from something like that might happen. But set these up, because if you set up the VM scale set, again, that means you're scaling automatic, rather than you having to go in and say, hey, I'm noticing I'm getting a lot of CPU utilization, we're getting a lot of traffic, I want to go start up a machine. That's manual. You have to do that. We talked about automation. This does the automation for you. You set the rules for it, and it will do it automatically. So, a couple things you need to know about VM scale sets. So VM scale sets, like everything, have limits. So everything has limits. The only question is, what are they? In this case, 100 machines are currently the limit with a VM scale set. So if you're running an application, like a very large web application, for instance, you may use more than 100. That's fine. You just set up multiple VM scale sets. That totally works. So set up multiple VM scale sets, and again, don't want a single point of failure. So even if you're not doing that, you may say, okay, I only have 50 machines. Great. Set up 2 VM scale sets, and set up 2 VM scale sets, each targeting 25 machines. You'll still have the 50 machines, but now you're protected. If one of those fails for some reason, something happened with your VM scale set, you've got a backup for it. It's all about the redundancy and about building that into the systems. So in this case, you can see I've got 1 VM scale set. Again, put it behind a load balancer. Load balancer is the back-end pool. You can point it at that. In this case, I used 3. You could do 2, you could do 3. But in this case, we're all in one region, and I now have the redundancy both at the VM scale set level as well as at the virtual machine level. So let's take it to the next level. OK, that was great for one region. What about multi-region? The answer is the same. You're going to do the same thing by region, but you're going to set it up in each region, and then you're going to use Traffic Manager, and Traffic Manager is going to point to the load balancer in each of those regions. So now you're being able to spread your traffic across those 2 regions and have redundancy both at the region layer and within the region layer. So more redundancy, slightly more complexity, but allows your application to handle bigger and bigger faults. So next one is network. Let's talk about the network. So load balancing. Everyone's using a load balancer, right? Yes? Sorry, I love these. Easy way to find it. Like, always use a load balancer. So it's important to understand the difference between a layer 4 and a layer 7 load balancer. In Azure, we offer you both. So if you use the Azure load balancer, both internal load balancer or the software load balancer, which faces externally, you're using a layer 4 load balancer. Now, what that means is that it's working at the packet level. So it's taking the packets and it's just routing them fast as can be. It moves them around. It's very scalable, very efficient, and it will take whatever traffic you put in. It's not only for things, many people are familiar with layer 7 load balancers, which in most cases normally deal with things like HTTP, which is great, but sometimes your traffic isn't HTTP. You might be dealing with a different protocol. So this allows you to load balance all of your information on that. But there's things it doesn't do. A lot of times people want a layer 4 load balancer, or they might want a layer 4 load balancer in addition. So if you want an HTTP load balancer, something like Application Gateway, we'll do things like Ssl offloading. Now remember, SSL is only there for HTTP, so it's not there for all your different packets. And so you need to understand that you can do that SSL offloading. Application Gateway is the way to do that, and that's a layer 4 load balancer. Now, you also may choose their third parties. I've listed a number of them here, Nginx, HAProxy, some of the kind of open source equivalent ones. You've also got proprietary ones from F5 and Barracuda. They're available in the Azure Marketplace. And there's great reasons why you might want to choose these, but if you choose to do them, you're going to need the architecture that I've shown up on the slide here. And this is actually what Application Gateway does under the covers. We do it all for you so you don't see it, but this is what we're at that point of failure. So what happens if a server fails? Well, I get to do here what I always would want to do in production but never would, which is I'm going to go in, and so this these happen to be running on Linux, but it'd be just as true if you're running IIS. And I'm going, and Nginx is the web server that I'm using here. So I'm going to kill the web server, which is oddly satisfying, I do have to tell you. So you kill the web server, it's dead. So now what happens? Well, let's flip over to the page, and we'll load the page. And I can keep hitting refresh, and you notice I'm only going to hit server 2. Why? I just killed server 1. Of course I'm only going to hit server 2. So that happens right away. So that's what you do when I'd say, put things in availability set, put them behind a load balancer. This is why. You fail over instantly. And so there you go. So I have the other machine up there, and it's running away, and it will serve, it'll serve these pages until I bring another one up and put it into the load balancer. But remember, we wanted to talk about, different blast radius. What are we protecting ourselves against? I protected myself against one machine taking a hit here. Well, gee, what happens if I then decide to be ultra nefarious and go take the other one down? So now I've killed our second web server. So we saw we were going through a load balancer. We saw I would only hit those two different ones, and now they've all gone down. So what I've kind of created an example of is what would happen if there was a region-level service disruption, if I had something that impacted all of them. Now what's going to happen to my web application? And of course, that's a teaser that I'll get back to. Because I want to talk through some of these pieces. So what do you do if a region fails? That's what essentially I've just kind of shown you, is I created a region failure by just taking down all the resources that are in that region. So this is one you can kind of think through to yourself of, what would you do? Would you use a load balancer to shift to additional resources? Would you use Azure DNS, point at a paired region? Would you use Traffic Manager to change the regions? Would you start up, if you're using Azure Site Recovery, would you start your runbook and start a failover? And then, of course, you could always just go complain to Twitter if you like. One of these is probably going to be your most effective option that you go do. And what you're going to want to do is you're going to want to use Traffic Manager. Remember all the designs that I put up earlier? We always had those kind of arrows pointing at each other, and it was pointing at two separate regions. That's Traffic Manager. That's kind of part of Azure DNS. Separate than Azure DNS, but it works together with it. And you're going to use that in order to be able to initiate your ability to move your traffic to a different region. So it works. You can conceptually think of it like a load balancer at the DNS level, but it works differently. And I want to talk to you about how that works, because it's important that you understand how they're different. And don't just think of them, they're load balancers, they work just like the software load balancers. So I'm a visual person, and I love animating slides because that's how I learn. So hopefully this will help you kind of understand what Traffic Manager actually does. So we've got Traffic Manager on the left here, and we've got your virtual machines on the right. So Traffic Manager basically just hollers out. It's like, hey, you there? And it does that through an HTTP GET. Just sends a GET across, and you can specify that in Traffic Manager, what the address is, what you want it to do. It's usually good practice to have that point at a status page. You can put it at your regular application if you want. The reason why you'd want to do a status page is because the status page one, you don't have to exercise the whole infrastructure if you don't want to. You may be doing transaction stuff. It allows you to just see, is it up? But also a status page, you can do something smart with it. You can have it monitoring your entire infrastructure and change the status that it returns based upon the whole infrastructure. If you just hit the front end page, your database could be down. The front end page still returns an HTTP 200 code. Everything looks good. And it thinks that your application is up and running, even though your application isn't up and running. It's not actually functional. If you have a status page and you've set that application to actually check the different layers of your application, and if those all don't work, it doesn't return a 200 status code, then it can actually be smart about when it does the failover and how it does it. So that's a best practice that you should do. You don't have to. You can just point it at the front end if you want. That's what I did for this application, because there's no database behind it. But it's going to respond. So the machine's like, yep, all good. Here's your 200 code, ACK. It's all good. So that happens. It gets 10 seconds to do that. So it waits 10 seconds for that response. And then it basically chills for 20 seconds. It hangs out. So basically you got 30-second intervals. And then it says, you know what happens if we kill the machine? So that's what we just did. We just took down that region. So it can't access that anymore. Well, Traffic Manager is really good at doing one thing and does the same thing over and over. It's like, if you've ever had one of those like drinky birds that sits there and just like drinks the water, goes back and forth, that's what it does. And so it only knows one thing. The whole world's a nail, it's a hammer. I'm going to go request it. So it goes and it sends it over again. But now the machine's not there. That region is unavailable, or at least your resources in it are unavailable, just like what we just did. So it gets no response. Waits for 10 seconds, doesn't get it. OK, no response. I'm going to wait for 20 seconds. Tries it again. Still no response. Tries it again. Tries it again. So it's going to keep trying. It always keeps trying. That's all it does. But after 4 tries, it says to itself, 4 tries, nothing's happened. So remember, it takes 10 seconds to wait for the timeout, 20 seconds in between, so you got 30 seconds, or 30 seconds as a whole, times 4, it's 2 minutes. After 2 minutes of getting nothing back, it finally gets a clue. And it's like, okay, this thing's actually down. It wasn't a lost packet, it wasn't something that was just a temporary blip. This thing isn't responding anymore. So I'm gonna go and I'm gonna update DNS. And it goes and it changes your DNS. Now it changes it to what you've configured it to. So you configure it. So you configure it to your secondary site. That's your second region, or third region or fourth region. You can choose what you want. But it goes and it updates DNS. So when someone makes a request now, it's gonna get that new request. But there's also a thing called TTL that you need to be aware of. So TTL is time to live. And what that means is that's how long that when someone's made a request to your server, that it should hold on to that. Because our servers all think in numbers, IP addresses. We usually think in names. So when I'm doing something like the Traffic Manager demo, trafficmanagerdemo.com, it's gonna know that, and it says, I don't want that latency, and I don't want that load on my DNS for it to look it up every single time someone's doing a request. So the TTL is how long it holds on to that. How long should your clients hold on to that before they re-request it from DNS? The default with Traffic Manager is 300 seconds, does it in seconds. That's 5 minutes. So it can be up to an additional 5 minutes before the client that's requesting this actually gets access to it. But the TTL is configurable. Like I said, 300 is the default, but you can lower that as low as 30 seconds. So you can drop that to 30 if you want. The benefit is these things will update faster. The downside of that is you're going to have more hits that go to your DNS. There's going to be more latency as more requests go through on that. So you have to strike that balance on what you want to do. If you're looking for kind of a quick, easy way of like, hey, is there any way I can short circuit this? There is. So I've set this up. You can set up Traffic Manager to work different ways. You can choose performance-based routing, or you can choose round robin, or you can choose weighted, if you want to weight things between two. So you can cheat a little bit if you want to, if you're actively managing it, by changing it to weighted, and then just weighting the other region much higher. Weight the other region 100, rate the region that's down to 0, and then it'll switch over faster. But if you're not doing that, if you're letting the system just run, it happens at a time when you're not monitoring it, it'll happen, and it'll wait for the TTL to end. Now for the person that just got it a minute before, it's going to take the full TTL time. For someone who's just requesting, it'll happen instantly. So realize that there is a gap there, and the gap is going to vary depending on what the client that's accessing it. So it goes, it updates DNS, and of course now your clients can go through. What happens when it comes back online? The different ways. Performance is basically it's using latency. It's seeing or the equivalent thereof based on the technology that we're using, but your scope of what could fail somewhere else. And then finally, you've got RAGRS, which is the same thing as GRS, disks that you're running that's actually your C drive. Say, for instance, in Windows, if it's not able to access it, it'll automatically retry the secondary region for you. Just makes it providing that isolation. And also providing the, but you have to be smart about it. So one, never put more than a JSON call in, that's basically the URL for your storage account, and it'll return a JSON blob that goes through, the other ones are queued up behind it. Now, the downside to that, and so it makes sure that within your session, it's there. I talked about before, asynchronous between the two processing, and it moves it off of your 8 megapixel pictures, and I haven't done anything like gzipping. And the neat little trick to it is all the servers that you shut better, it helps me provide better information to the people. Oh, sorry. Yes?
So for availability sets?
Yes.
Coming up, we take a look at how Azure Serverless offerings allow you to build and deploy elastic-scale, cost-efficient apps on Azure. We'll show you how adopting a serverless compute approach removes the need to worry about hardware resources and the operational complexity of running applications, the event-driven model for triggering compute power that allows you to just pay for what you use, and we'll walk through a serverless app for social analytics. I'm joined by Jeff Holland from the Azure Serverless Compute team. Welcome.
Thrilled to be here.
So serverless computing seems to have picked up a lot of momentum over the last year, but what is it and why has it come about?
Yeah, so it's a response to a number of things, but mainly it's around removing traditional barriers and building and deploying software to solve business needs. Traditional apps are designed to conform to the infrastructure they run on. Serverless apps offer an app-first model by abstracting away the infrastructure to relieve the developer from the operational complexity of running applications. the infrastructure only fires up when it needs to. It's serverless because you no longer have to worry about servers, virtual machines, patching, scaling, all those pieces that traditionally you have to manage and take time away from creating solutions. With serverless, you simply define your code or the steps that need to happen, publish it to Azure, and the rest is automatically taken care of for you. This means you can build and deploy cloud scale applications in a fraction of the time.
Now, what you just described sounds a lot like PaaS, but how does this differ from platform as a service?
How to build
So with PaaS, you still have to choose
faster
your
with
operating
Azure
system and
Serverless
VM
that is
size,
been covered
which
in
means you
this
need to be able to
video.
forecast your demand
Just
and then
light
pay
is
for that
been thrown in
capacity,
this.
even if it's not fully utilized.
So how does this actually work in Azure?
With serverless, Azure has compute resources ready to be allocated to you. Their usage is triggered by an event. You give us your code, and when an event happens, this could be an Azure alert or when a message is received, whatever you specify, we spin up the necessary compute resources, and it's activity-based billing, so you only pay for when you're using the resources.
So can you give us an example and explain the serverless tech architecture behind this?
Sure. If I have a website and people want to upload pictures, let's say I need to resize those pictures. So whenever someone uploads a picture, I want to automatically resize it. Well, the upload is the event, and that's where Azure Functions come in. It contains and runs your code to resize the picture, and it has a series of bindings that attach to the event you want to listen to. So in this case, it listens for an upload and automatically resizes the image.
So I'm a developer, I've got my chunk of code, I give it to Azure Functions and it executes.
Yeah, that's exactly right.
But what if I need my code to perform multiple tasks? So if we stick with our photo example, so resize, compress, create a thumbnail, and then upload it to a store.
Yeah, so each one of those individual tasks would be an Azure function. And to orchestrate these different tasks, I would use Azure Logic Apps to build a workflow. So in our example, the different tasks from resizing, compressing, creating a thumbnail, displaying it in the store, those would be executed on an uploaded picture. And once all these tasks are done, I could make the next step to store the picture in OneDrive or my chosen cloud storage. And what's great is that most of the time, I don't even need to write the code for the orchestration or to integrate with apps like OneDrive because Azure Logic Apps has pre-built connectors.
So developers can just focus on their blocks of code and they can utilize these connectors to integrate with their existing systems.
Yeah, exactly. So I'm showing here, there's over 150 connectors provided by Logic Apps today. And this allows me to easily bind my serverless app to listen to events from sources like Dynamics or Salesforce. And I can also very easily create or push data into any of these sources.
Now, a lot of these connectors and what they connect to, they'll be familiar to IT. So it's important that both IT and developers work closely to integrate these in a way that's right for the business.
Right. In fact, a lot of the value that IT finds in systems like Logic Apps is that it allows them to very easily integrate those apps that their devs are building with the systems that they manage.
So it sounds powerful, but can we see it in action?
Sure. So I'll walk you through now the tools needed to build a serverless app. And in actually just a few minutes, we'll actually have something pretty powerful up and running. So in our case, we're going to listen to a data source, which is Twitter. We're going to be listening for different tweets. So maybe there's a conference or a launch that you are interested in understanding more about. So as tweets come in, we'll analyze them and publish them into a Power BI dashboard, all in real time. So I'm here in the Azure portal, and this is the start of our app, and we're going to use that serverless workflow, Logic Apps, to start building our serverless app. So you'll notice here I've already added the event, which is when a tweet is posted. And in this case, I'm actually listening to tweets about Microsoft. Now, I can start to add in actions and resources to spin up when this event happens. So I'll go ahead here and add a step. And you'll notice those connectors we referenced earlier. And here I'm actually going to choose the text analytics connector, which uses machine learning as part of the cognitive services to actually do advanced things like detect the sentiment or pull out key phrases. So within just a few clicks, I could pass in the tweet text, and now just that easily, I've added machine learning into my serverless workflow. So at this point, I have the tweet, and now I've been able to automatically detect if it's positive or negative. So this is a great place for us to now add in an Azure function, because maybe I want to set a category like red, yellow, or green based on the sentiment. So I can go ahead here and add another step. And here I can choose any of my Azure functions to execute on demand. So I'm going to go ahead here and choose an Azure function which I wrote ahead of time that will categorize the tweet based on the sentiment score. So the sentiment service will give it a number between 0 and 1, 0 being very negative and 1 being very positive. So I'll actually show you what this Azure function looks like. So this is an Azure function in the portal, and you can see it's very simple. I've just simply had to define my trigger event here, which will be triggered from a logic app. And then I just wrote the simple code. So if the score is below 0.3, it's red. If it's below 0.6, it's yellow, and everything else is green. And just that easily, I've defined the code, and now it will run whenever it needs to.
So what's happening here behind the scenes from a resource allocation and utilization perspective?
Yeah, so resources will be deployed on demand as needed. So I'll actually switch here. There's a function that's been running all day today, and I'll show you how it's running, and it's running pretty heavily. So it's automatically spanned a number of different servers to handle that execution. What's great is that I only defined the code, and these servers have been provisioned and scaled out to meet demands automatically, and I'm only paying for what I use.
And it'll auto scale as necessary. You don't have to worry about anything infrastructure related.
Exactly.
And this is what we saw before, C# code, but are other languages supported?
Yeah, so if I create a new function, I can actually choose from a number of different supported languages, like C#, PowerShell, JavaScript. This enables me as a developer to use the language that's best suited for the job, and I can build, deploy, and debug these serverless apps all within Visual Studio.
But now can you go ahead and visualize the data?
Yeah, exactly. So here I'm going to come back to our serverless app, and I do want to visualize the data that I've generated. So I'm going to add in one more action. And in this case, I'm going to use our Power BI connector to publish this data to a dashboard in real time. Now, while I fill out this step for the Power BI connector, I do want to call out here that I am connected to my Power BI account. And we take security very seriously, so we use Azure Key Vault behind the scenes to securely encrypt and store the credentials needed to authenticate with this service. So whenever OAuth is provided, we always use OAuth, and if OAuth is not available, we use whatever means is most secure.
And because we're connecting to data that's critical to running your business, it's great to see that secure connectivity is just built into the serverless platform.
Yeah, that's right. And as you're connecting to multiple disparate data sources, we want to make that as secure as possible.
So what happens next?
Yeah, so I'll go ahead here and finish pushing this data to the Power BI connector, things like that category that we generated from the Azure function, the location of where the person is tweeting from, and when this tweet was created at. And what's powerful here is now I've created this, and I can simply click Save to publish it, and it will start triggering on those events from Twitter. So I'll go ahead now and switch to this Power BI dashboard, and in just a few seconds, you'll start to watch this dashboard light up as people are tweeting about Microsoft. Those tweets are being processed automatically by our serverless app and scaling up the resources needed to process those requests. Now, if this was during a high time of traffic like Microsoft Build, I have confidence in knowing that my app could automatically scale to meet those demands.
Can we see another app?
Yeah, so I'll actually show you, I've taken an app very similar to this. It starts the same way, but I've added a few more steps. So after I published to Power BI, I've actually added in some logic here so that if somebody tweets a very negative sentiment tweet, I can automatically do something like alert a team using Microsoft Teams or create a case within Dynamics 365 so that my company can be monitoring the customer sentiment and following up with customers on Twitter.
So now the app is deployed. How do we ensure that it's tested and ensure it's running efficiently on an ongoing basis?
Yeah, so this isn't like traditional infrastructure where you can look at processor utilization or other metric. So it all comes to life with a trigger. And as you're building the app, you're running tests to simulate the event, triggers to make sure the app that work in the way that you want. And with that, serverless apps do come with a lot of tracing out of the box. So I can easily see here from right within Azure, all of these apps as they're running and understand the data that's being processed. And I get integration with powerful tools like Azure Monitor so that I can view metrics or diagnostics, set things like alerts for if something goes wrong. You saw me show this earlier, but I can use tools like Azure App Insights to understand the health of my app, and even integrate with solutions like OMS so that I can do query analytics and understand exactly how my systems are performing against my solution.
So with Azure Serverless offerings, you're getting a fully managed service that scales on demand and run your apps in a fraction of the time. But how do people get started with Azure Serverless?
Yeah, so we have a few quick starts on the Azure Functions and Azure Logic Apps documentation pages. And what's great about serverless is you can spend just an hour or two and have some really powerful apps ready to go. So I'd encourage you to check it out, reach out to us on Twitter if you have any questions, and see what serverless computing and Azure can do for you.
Awesome stuff. Thanks for joining us, Jeff. And don't forget to keep watching Microsoft Mechanics for the latest in tech updates. See you next time.
While searching, I found one book related to this. That is nothing but Building Elastic and Resilient Cloud Application. So it is a developer's guide to the enterprise library integration pack for Windows Azure. Okay, so if you want to go into the details of it, it will be covering the things like yeah. So here it will cover the introduction to Windows Azure with about then developing Windows Azure application, managing, monitoring and debugging things, then introduction to enterprise library integration pack for Azure, auto scaling and Windows Azure. What is this auto scaling is, so the details of it will be covered. Then making tailspin surveys more elastic. So individually how to go with implementation of each and every part. So that is been covered here and how they are being deployed. Then transient fault handling. So that part already some of the features now in the video are being covered, how to handle the conditions. So making tailspin surveys more resilient. So its details are given over here. So these are the parts that are being covered in this book. So how to set up this kind of an environment and all. So that part is covered here. Pooja Birazdar, your video is on. Okay, so much of the part related to deployment and that are being covered in the videos like today's video and whatever we have seen in yesterday's video. So that part is being covered now. So we are pending with this kind of infrastructure for okay, so now from this chapter, this designing of elastic, highly available, resilient infrastructure for varied application using Google Cloud platform and the financial and technological implications, that part is now remaining from our side. So that will be covered on in our Thursday's lecture. Today is Tuesday, and then I will end up with this particular unit. So much of the part is absolutely practical oriented over here, but whatever the questions I found which are used from the theory paper point of view, and whatever the MCQs I found, I will share with you. After this point, we will have a class test on this unit so that we can get into the details of it. Okay, so for now, we will stop over here. If you have any doubt, please raise your query or ping me personally. Otherwise, we will stop over here. Okay, thank you. Put your attendance in the chat and then you can leave. Thank you. Tajmin, Sarika Hande, and Pooja Birazdar, put your attendance. Varali, you joined now only. Put your attendance and leave. Sarika. So we will end up with the lecture for today. We'll meet on Thursday in our next lecture. Thank you.